You might have been written a nice piece of code. It works totally fine on your local PC, but when you upload your code into the powerful servers, let's say a server with 2 CPUs and each CPU has 16 cores, the performance of your program tanks. That is NUMA, or non-uniform memory access. So, hello everyone. Welcome back to the series of what every programmer should know about the memory. So far we've talked about stack, heap, paging, virtual memory, and CPU caches. But today we are looking into something that becomes really critical when you want to scale your program. By the end of this video, you will learn what NUMA is, how it matters, and how to write NUMA-aware code that performs best in the scalable machines. Let's get started. In the early days of computing, when systems they have only one CPU and one memory, everything was much more simpler. Every CPU instruction that needed data would reach to the RAM in order to find it from the big pool of RAM which is shared between all programs inside that machine. All memory accesses had the same cost. This model is called UMA, or Uniform Memory Access, and it made sense for a while. But then with the advancement of technology, everything got fast. We added more cores, more sockets, and at the end, all of these CPUs talking to the same memory causes a major bottleneck in the system. You had multiple CPUs trying to access the same data lanes, like cars trying to merge into the one-lane highway. To solve this problem, hardware engineers introduced NUMA. With NUMA, memory divided into the different regions, and each region is closely tied into a specific processor or groups of cores. This is what we call NUMA node. NUMA exists because it can help us to scale memory bandwidth across sockets and reduce contention. But the trade-off of it is the complexity. If you don't manage memory placement and thread affinity, you could be paying double or triple the latency for every single access. When your program allocates memory, the operating system decides which NUMA node's memory to use. And when a thread accesses that memory, it either hits local memory, which is great, or it ends up reaching across other memory, which is bad and slow. Think of it like this. Imagine a multi-socket motherboard. Socket 0 has its own RAM bank, and also socket 1 has its own RAM bank too. If a core on socket 0 accesses its own RAM, that access will be fast. We call it local memory. But in the case that this core tries to access a RAM on socket 1, it has to go through a special interconnect, which is basically a remote memory, and it is much slower. Accessing memory locally may cost around 80 to 100 nanoseconds, but in the case of remote access, you may face 200 to 300 nanoseconds. Multiply that by millions of access in a loop, and your application runs even slower than your local machine. And this is the worst part, because you cannot debug this on your local laptop because you don't face it there. But every time you upload your program into the server, which has 2 or 4 sockets, for example, you will face every time that your program slows down, and things can get ugly very fast. This is why many high performance apps like databases, video encoders, machine learning algorithms, they are all NUMA aware, and yours should be too. Writing a NUMA-aware code means 2 things. One, you need to make sure that your threads are running to the CPUs closest to the memory that they need. 2, you make sure that the memory is allocated to the same NUMA node as the thread that will use it. Let's look at both. The first one, we call it thread affinity. When a thread is created, the operation system might move it around into the different cores, even across different sockets. That means the thread can run today happily on core 2, everything looks perfect, but tomorrow when you run your program, the thread will run on core 10, and it constantly accesses the remote memory, which means that your program slows down. To stop this, we use CPU affinity, and we basically pinning threads to the specific CPU cores. In C++, as you can see in this example, we pin the thread to core 0, and by using the pthread set affinity and p function, we make sure that thread is always running on that CPU core. Or from the outside, you can run a whole process like this. This forces the process to use only the CPUs from node 0. The second one was memory allocation. So here is the sneaky part. Even if you pin a thread to a specific CPU core, the memory that it accesses might still get allocated on the remote node. By default, Linux uses first touch policy, which means the page that is allocated on the NUMA nodes of the CPU that first writes to it. So if one thread initializes the memory, but another thread actually uses it, that's a classic remote access problem. You can solve this by either making sure that the thread that will use the memory will also initialize it first, or you can use APIs like libnuma library to allocate a specific memory to a specific node. For example, in this code, it will allocate 1 megabyte of memory on node 0. Or if you prefer a command line tool, you can run your application with this command. This ensures that all memory which is allocated to your program is from node 0. Okay, we are talking about this remote memory access, but how can we recognize if our program is accessing remote memory instead of local memory? Linux gives us a tool called numastat. You can run your application like this. You will get a report showing how much memory your process is using from each NUMA node. If your app is pinned to use only node 0, but you see a bunch of accesses to the node 1, then it means that your app has a problem. And trust me, there are a bunch of examples that the programs are using 90% of remote access, which by just solving this, it could double the performance of the application. So to wrap up, NUMA is basically doesn't matter at all until it really does. On a small machine, you might not even feel it. But on a big server with multiple sockets, NUMA can bite you back. And that means a huge cost for you. If you want high performance, your thread and the memory that you are using needs to be close to each other. NUMA-aware programming, it's not just a nice thing to have. It's essential for serious works like in databases, machine learning algorithms, simulations, renderings, and any system that lives on the multi-core CPUs. So if you have ever experienced such NUMA-related problems, I'm curious to hear about it in the comment below. Until the next video, good morning, good afternoon, and good evening. Bye.